Welcome back to another episode, my dear friends. Today, we are going to talk about something really important and a simple concept, that is the Eigen vectors.
Last time I've asked you people, what does mathematics mean to you? And some have answered that it's the manipulation of numbers and manipulation of structures. And if I had asked what music means to you, would you have answered the manipulation of notes? Eigenvalues and eigenvectors is one of the topics that most of the students find unintuitive. Questions like why we are doing like this, what does this actually mean? It is not that eigenthings are particularly complicated and poorly explained. In fact, it's comparatively very straightforward, and I think most books did a very good job in explaining this. The issue isn't really made sense if you have solid visual understanding from many of the topics that preceded. Most important thing here is you know how to think about matrices, linear transformations, but you must also be comfortable with the things like determinants, linear systems, and change of basis.
Now, let's get started with our lecture and get a clear understanding on this eigenvalues and eigenvectors. In linear algebra, an eigenvector, also called a characteristic vector of a linear transformation. This is a non-zero vector that changes at most by a scalar factor when that linear transformation is applied to it. This corresponding eigenvalue is the factor by which the eigenvector is scaled. To define eigenvalue and eigenvectors formally, it is defined as if T is a linear transformation from a vector space V over a field F into itself and V is a non-zero vector in V, then V is an eigenvector of T. If T of V is a scalar multiple of V, this can be written as T of V is equals to X into V, where X is scalar in F, known as the eigenvalue or characteristic value or characteristic root associated with V. If V is finite dimensional, the above equation is equivalent to A into U, that is equals to X into U, where A is the matrix representation of T and U is the coordinate vector of V. The Mona Lisa example pictured here provides a simple illustration. Each point on the pointing can be represented as a vector pointing from the center of pointing to that point. The linear transformation in this example is called as shear mapping. Okay, do you understand the concept until now?
Yes, sir.
Alright, this is the complete overview of the chapter Eigenvalues and Eigenvectors. Now let's get started with the history of eigenvalues and eigenvectors. Eigenvalues are often introduced in the context of linear algebra or matrix theory. Historically, however, they arose in the study of quadratic forms and differential equations. In 18th century, Leonhard Euler studied the rotational motion of a rigid body and discovered the importance of principal axis. At start of 20th century, David Hilbert studied the eigenvalues of integral operators by viewing the operators as infinite matrices. The first numerical algorithm for computing eigenvalues and eigenvectors appeared in the year of 1929. Now let us know about the eigenvalues and eigenvectors of matrices. The topic is often introduced to students in the context of linear algebra courses focused on matrices. Furthermore, linear transformations over a finite dimensional vector space can be represented using matrices, which is especially common in numerical and computational applications. This is one such graph which explains the eigenvalues and eigenvectors of matrices. Now let us see some dynamic equations of eigenvalues and eigenvectors. In the first dynamic equation, we can see that the trace of A defined as the sum of its diagonal elements and is also the sum of eigenvalues. And in the second one, the determinant of A is the product of all eigenvalues. And these two are some simplest differential equations. And let's see some of the iterative methods to solve the eigenvalues and eigenvectors. One of them is this one. In this, if V is an eigenvector of A, then the corresponding eigenvalue can be computed as lambda equals to V star AV by V star V, where V star denotes the conjugate transpose of V. It is very much important to know the applications of any concept we learn to apply it perfectly. Eigenvalues and vectors have a wide range of applications. For example, in stability analysis, vibration analysis, atomic orbitals, facial recognition, and matrix diagonalization. Schrödinger equation is an application of eigenvalues and eigenvectors. An example of an eigenvalue equation where the transformation is represented in terms of differential operator is the time-independent Schrödinger equation in quantum mechanics. Molecular orbitals are also an application of eigenvalues and eigenvectors. In quantum mechanics, particularly in atomic and molecular physics, within the Hartree-Fock theory, the atomic and molecular orbitals can be defined by eigenvectors of Fock operator. Geology and glaciology are one of the major applications of eigenvalues and eigenvectors. In geology, especially in the study of glacial fill, eigenvectors and eigenvalues are used as method by which a mass of information of a class fabric's constituents orientation and dip can be summarized in 3D space by 6 numbers. Eigenvalues and eigenvectors are even applied in principal component analysis. It is also one of the major applications of eigenvalues and eigenvectors. This is all about the second chapter, Eigenvalues and Eigenvectors. Meet you in the next class with a new lesson.